let's ask a really big question. What is everything actually made of? I mean, if you could zoom in, way in, past your skin, past your cells, what would you even find at the very bottom? Well, today we're going on that exact journey. We're zooming right into the fabric of reality itself. But first, a little warning. I've heard you shouldn't trust atoms. Why? Because they make up everything. Okay, it's a classic science joke, I know, but it's also the absolute truth. These incredibly tiny particles are literally the building blocks of our entire universe. So what really is an atom? While the official definition says it's the smallest possible piece of an element you can have, if you slice it any smaller, it just stops being that element. Think of it as the ultimate Lego brick. You can't break the brick itself down any further and still call it a brick. And that leads us right into our first big idea. It sounds simple, but trust me, this is the foundation for pretty much all of modern chemistry and physics. So here's the bottom line. Anything you can touch, see, or smell, it's all made of atoms. Now, when you get a chunk of something that's made of only one type of atom, like a bar of pure gold or a tank of pure oxygen, we call that an element. And when different kinds of atoms link up, like two hydrogen atoms grabbing onto an oxygen atom, they form a molecule, and in that case, you've just made water.
All right, so we've established that atoms are the basic building blocks. But what's inside the block itself? For the longest time, people just figured they were tiny, solid, unbreakable spheres. But the truth is so much weirder and more interesting than that.
And this is the million-dollar question, isn't it? Atoms are ridiculously small. You can't just slice one open and peek inside with a microscope. So how on earth did scientists figure out their structure? Well, the answer involves a super thin sheet of gold foil and one of the most brilliant experiments in history.
This is it, Rutherford's gold foil experiment. The idea was simple but genius. They basically built a tiny little cannon that shot out positively charged bits called alpha particles, and they aimed this cannon at a piece of gold foil so thin it was only a few hundred atoms thick. It was literally like firing cannonballs at a sheet of tissue paper. What they saw next was just completely unexpected. I mean, it blew their minds. Almost all of the little particles zipped right through the foil like it wasn't even there. A few of them got knocked off course a little bit, but, and get this, about 1 in every 8,000 particles bounced straight back. Rutherford himself said it was as unbelievable as if you'd fired a cannonball at a piece of tissue paper and it came back and hit you. This one shocking result unlocked 3 huge secrets about the atom. First, since most particles went straight through, the atom had to be mostly empty space. Just nothing. Second, for a particle to bounce back like that, it must have hit something incredibly small, super dense, and positively charged. They call this the nucleus. And third, to keep the atom neutral, there must be some negative particles, electrons, orbiting that nucleus somewhere out in all that emptiness. And so this brings us to the 3 fundamental particles that make up an atom. You've got your positive protons and your neutral neutrons hanging out together in that dense little nucleus. They both have a mass of about 1. And then you have the electrons, these tiny negative particles whizzing around the outside with, you can see, almost 0 mass at all. They're incredibly lightweight. Okay, so we know what's inside an atom, but there are over 100 different types of atoms, 100 different elements. How do we keep them all straight? Well, luckily for us, humanity came up with one of the most elegant and powerful cheat sheets ever created. And here it is, the periodic table of elements. Seriously, this thing is so much more than a colorful poster in a science class. It's a masterpiece of organized information. Every single building block of matter that we know of is on this table, laid out in a way that reveals the universe's deepest patterns. The logic behind it is just beautiful. The elements are arranged by their atomic number, which is just a fancy way of saying the number of protons they have. Anything in the same vertical column or group acts in a really similar way chemically, and everything in the same horizontal row or period has the same number of layers of electrons. It's an unbelievably predictive map. Now, atoms like to be neutral, right? Same number of positive protons and negative electrons. But they're not always stable. They can gain or lose electrons, and when they do, they become charged particles we call ions. If an atom loses an electron, it has more protons than electrons, so it becomes a positive ion, or a cation. If it gains an electron, it becomes a negative ion, an anion. And here's something you might not expect. This change in electrons actually changes the ion's size. when an atom loses electrons to become a cation, it actually gets smaller. Why? Because now there are fewer electrons, and the positive nucleus can pull the remaining ones in even tighter. On the flip side, when an atom gains electrons to become an anion, it gets bigger, because that extra negative charge pushes all the electrons a little further apart. And if you're ever struggling to remember which is which, don't worry. The internet has got our back. Just remember this cat. Cations are positive. See? Now you're never going to forget it.
Okay, let's get back to the periodic table, because like I said, it is so much more than a list. The way it's structured lets us predict how elements will behave without ever touching them. It's just loaded with hidden patterns and trends. Let's take atomic size, for example. There's a clear trend. As you go down a column, atoms get bigger. And as you go from right to left across a row, they also get bigger. So the biggest atoms are down here in the bottom left. Just look at the image on the right. See how tiny fluorine is compared to the big ol' cesium atom? The table tells you that at a glance. And here's another great trend, ionization energy. It sounds complicated, but it's just the amount of energy it takes to steal an electron from an atom. And yep, there's a pattern for that too. It's really hard to steal an electron from the elements in the top right, like helium. They hold on tight, but it's super easy to snatch one from the guys in the bottom left, like cesium. So, we've explored the atom's core, the nucleus, we've talked about the amazing organization of the periodic table, but we have absolutely saved the strangest, most mind-bending part for last. Those tiny electrons whizzing around in all that empty space. To understand electrons, you actually have to understand light first. We typically think of light as a wave, right? An electromagnetic wave, with these electric and magnetic fields dancing with each other as it flies through space. It's pure moving energy. But, and in physics there's always a but, things get weird. An experiment called the photoelectric effect showed that if you shine a light on a piece of metal, it can literally knock electrons right off of it. This proved that light doesn't just act like a wave, it can also act like a particle, a little packet of energy. It has a dual identity. So think about that. If light itself is living this bizarre double life as both a wave and a particle, what does that mean for the electrons it's interacting with? Well, it turns out electrons have a secret identity too. And that revelation opens the door to the truly strange and wonderful reality of the quantum world, which governs everything. It just makes you wonder, what other secrets are these tiny building blocks hiding from us?